Hello, everyone. I'm Matt Hansen. I'm a Principal Solutions Architect with AWS Robotics. Joining me today is Justin Cyrus, the CEO of Lunar Outpost, and we're here to talk to you about how Lunar Outpost uses cloud-based simulation to advance robotics space exploration. First, we're going to give you some background on Lunar Outpost and its mission to bring payloads to the moon. Then we're going to discuss some of the challenges for building robots that will run in space, and how Lunar Outpost uses AWS to develop, test, and run their robots in space. Finally, we'll do a deep dive on AWS RoboMaker and the new features that enable you to run high-fidelity simulations in the cloud. So next, I'd like to introduce Justin Cyrus. Justin, please take it away.
All right, thank you for the introduction, Matt. As he said, my name is Justin Cyrus, and I'm the CEO here at Lunar Outpost. To give you a quick background on Lunar Outpost, we were founded in 2017. We sold our first product less than 6 months later, and we've been off to the races since. We have NASA, AFRL, US Air Force, US Space Force contracts, specifically focused around advanced robotics and advanced spacecraft. In addition, we had our first contract with MIT on MOXIE back in 2018, and that instrument is operating on Mars today, creating oxygen out of the CO2 in the Martian atmosphere, which we're extremely excited about, and that is currently on board the Mars Perseverance rover. In addition, we have the first contract in human history on a space resources contract, and we received the first payment for that last month. We have 2 rovers that are going to the moon. The first is in Q4 of 2022 to the lunar South Pole. The second is in Q4 of 2023 on a soon-to-be-announced mission. So to give you a little bit more information on why it's hard to build robots in space. Not an easy task, and certainly a very expensive task, and we're trying to change that. Now, on the lunar surface specifically, you have negative 200 degrees C to plus 200 degrees C temperature swings, which is very hard to survive in, let alone operate. In addition, you have electrostatic dust and regolith that can clog some of your systems. You have a high radiation environment, and you have no current infrastructure support. So you don't have communications, you don't have power, you don't have an astronaut to pick it up and press the reset button if something goes wrong. So you have to bring a lot of that with you, at least for now. And this offers some developmental challenges as well. Current spaceflight hardware costs are very high, and representative hardware is expensive. And that allows, or I would say that pushes physical trials to be inherently risky, right? If you break a robot that costs a couple $1 million, that's one of your test articles, that can be a big deal, especially on a startup's bottom line. Now, as I said earlier, there is no possibility for intervention, or at least physical intervention. There are debugging steps that can be taken, software can be reflashed, but for the most part, when something breaks on the moon, it's broken. So we have to be very strategic on how we deploy and operate our robotic systems. Now, here is a quick rundown on our mobile autonomous prospecting platform. It's a 10 kilogram class system. 50% of that is payload mass. It is the size of a large shoebox and drives at around 10 centimeters per second. That might seem slow, especially when compared to electric vehicles here on Earth, but that's actually quite fast for a planetary rover. So this was a purpose-built prospecting rover that provides spacecraft as a service to partners and other payloads on board so we can accomplish the mission at hand. So to talk about our development with AWS, here are 2 services to kind of get us started. Amazon QuickSight, which allows our developers and our software engineers to have insight into improvement over time for our machine learning and our navigation algorithms. And Insight also allows for visualization of performance statistics for algorithmic iterations and our code commits as we build over time. Now, AWS RoboMaker allows for high fidelity simulated environments that really allow our team to iterate in an agile manner and test as we build on our systems. Now, something that's pretty unique to AWS RoboMaker that has our engineers extremely excited is the ability to operate and test swarms of our robots on the lunar surface, a high fidelity lunar surface, simultaneously. And as our development team grows, each member of the development team can access RoboMaker as needed. Now, here's a quick snapshot of the first service I was talking about. So as you can see, this is one use case of QuickSight for us. We are showing improvements to our navigation stack over time. The error is shown in that top graph, and it's shown, the first commit versus the last commit. The error goes down quite a bit, but you can see that the commit shown here, you still have quite a bit of difference between where the rover thinks it is, which is one line, where the rover actually is, which is another line, and where the command velocities tell it where it should be, which is another line entirely. So this is a great example of how QuickSight allows our engineers to take a quick look and say, hey, look, this is a problem, and this is something we need to be able to fix, and compare that to other commits and see how we can move forward. Now, this is part of a larger automated CI/CD pipeline, and a few of the AWS services involved include QuickSight, include Code Commit, Code Build, ECR, and AWS RoboMaker. Now, to show a later commit where our algorithms are doing a little bit better, you can see that the robot actually does a great job of localizing itself in this high fidelity lunar environment. So we can track that previous commit that we showed on the previous slide, compare that to the current commit, and show that large improvement over time. So whatever changes our engineers are making, they're doing a good job. Now, to talk a little bit about AWS RoboMaker. This is one prospecting mission, one simulated prospecting mission that our team ran. And now the features these robots are looking for and are categorizing as part of this simulation are rocks. Now you can change those features to be permanently shadowed regions, to water ice buried under the lunar regolith, what have you. But here the robots are working together to efficiently prospect the area that they're given. Now to move on to the next simulation, this is a large swarm simulation. And again, this is fairly unique to the cloud environment. You would not be able to run this locally, especially once you add in all the algorithms and the swarm interactions of the swarm. Now these robots are fanning out to efficiently prospect a large area on the lunar surface. And when one robot detects something of interest, and in this case, again, rocks, the other robots will note that it has detected a rock and will work their way over towards that general area, and again, efficiently work off of each other to prospect the area and find those features of interest. So here is a quick snapshot of our unified ground station tech stack. Now, Lunar Outpost does work with our lander providers and their ground station, and our onboard payloads and their ground station as well. So we need a way to securely and reliably receive and send data from our own architecture. Fortunately, many of our partners are already utilizing AWS, and a few more are coming on board. Now, this is a quick snapshot. Matt will talk a little bit more about this later, but please reach out if you have any questions. Now, here's a quick preview on mission control. This one is exciting to me personally. If you imagine a NASA mission control, you imagine 60 to 80 people sitting in a large room down in Houston, Texas, or down in Florida. But that's not necessarily what it needs to look like nowadays. Many organizations and many large organizations like Lunar Outpost and others are utilizing the cloud to basically be able to operate your rover from any environment. So that for us means we can operate our rover from our offices here in Colorado. We don't have to be in the same physical location as our lander ground station is. So that also allows us to have redundant operation centers, which can protect against power outages or internet outages, which unfortunately still affect space companies. So here's a mission control preview. Off to the left, you see a simulated environment where our rover is localized itself in that simulated environment based off of the data it's collected. Off to the right, you see the instrumentation data and the robotics data, and this allows our operators to see real time where they're at in the environment, what data they're getting back, so that way they can help the robot make the best decision moving forward. So what's next for Lunar Outpost? Well, first and foremost, we're really excited about utilizing AWS RoboMaker to create a digital twin forward simulation. This will be a first of its kind program, taking real live stream data from the lunar surface, porting it into AWS RoboMaker to give us here on Earth a real-time simulation where we can forward operate a variety of different algorithms from navigation to resource prospecting, etc. So that way we can help inform our robot operating on the moon to make the best decisions. We do have our upcoming missions. We have our first mission, as I've stated, to the lunar South Pole, launching in December of 2022. And the location was recently announced to be right outside Shackleton Crater, which we're extremely excited about. And then we have our NASA mission in 2023, which you'll see an announcement out of us here shortly. We do currently have a little bit of payload space left for our mission going to the moon, specifically the lunar South Pole mission in 2022. If you would like to learn a little bit more about that opportunity, please contact us at info@lunaroutpost.com. Additionally, if your payload isn't going to be ready quite in time for the 2022 mission, we would still love to work with you. What we can do now in combination with AWS is provide a simulated high-fidelity lunar environment for your payload to operate in. And we can run mission operations, concepts of operations to figure out not only what kind of data your payload can collect, but how it can interact with our robot and the lunar environment. In addition, if you would like to reach out and you're a space enthusiast or you're in the space industry or just the robotics industry, and you want to help contribute to the state-of-the-art knowledge on planetary bodies, our solar system, or our universe, please contact us at info@lunaroutpost.com. Thanks, Matt, and back to you.
Well, thank you, Justin. And now I'd like to give you an overview of how to run robotic simulations using AWS RoboMaker. First off, a little background on simulation and why simulation is important. And while simulation in robotics is relatively new, the concept of using simulation dates back to early civilizations. Roman armies trained their soldiers by recreating battle scenarios using wooden swords. One of the key reasons why the Roman army was so successful was their training. Practicing with wooden swords reduced the chance of injury and enabled them to work through various battle scenarios. Later on, in the Renaissance era, Leonardo da Vinci was known to build scale models of his inventions. He did this to test different configurations and quickly iterate, optimizing the design before building costly full-size prototypes. Today, simulation is used across almost every industry. In healthcare, surgical students learning new technologies practice everything from simple sutures to advanced robotic surgery before performing these operations on humans. In agriculture, farmers use simulation to determine land management strategies and adapt for the impacts of climate change. By running internal crash tests and simulations, car manufacturers can reduce the number of destructive tests they need to do with actual cars. Finally, simulation in aviation dates back to the 1920s. Today, flight simulators are a mandatory part of pilot training and used across the industry, from commercial airlines to space travel. The common result in all of these examples, from combat training in ancient Rome to NASA's rover pilots, is that simulation enables faster iterations and lowers the cost of mistakes. This leads to accelerated learning cycles and an increased pace of innovation. Simulation benefits are particularly valuable in robotics development and prototyping. First, robots can be costly, and access to robots during development can be scarce. By using simulation, every developer can easily access a virtual robot. And when unexpected behaviors happen, there's no risk to expensive hardware. Secondly, developers may want to specifically test for conditions that may be unsafe or risky to test in the real world. In simulation, you can also speed up the clock for faster than real-time testing, enabling developers to run tests that would be very time-consuming or not practical on actual robots. Next, you can expand the coverage of your tests in simulation with parameters that cover all the conditions your robot will encounter. For example, you could run a set of tests in 100 different room layouts. This would be very difficult to do with physical robots. When running simulation, you can easily repeat scenarios with specific conditions that led to unexpected behavior in the past. And by running regression tests in simulation, you can ensure your robots meet your customer expectations. Finally, teams can use simulations to decouple their development workflows, enabling various teams such as front-end UI, UX teams, robot software development teams, and hardware development teams to work in parallel without needing access to the physical robot to do testing. When robotics companies use simulation early in their development cycle, they typically have a faster time to market, an increased feature release velocity, and introduce less software defects during code iterations and in production. Today, we will talk about how AWS RoboMaker can make it easy for your company to get started with simulation today. So the development cycle for a robot application usually starts with simulation. Simulation enables all developers to easily access virtual robots to test applications and algorithms without requiring access to expensive physical equipment. AWS RoboMaker enables developers to run simulations in the cloud with a simple API call and can be integrated with automated test workflows. Developers will commonly iterate many times in a simulation before deploying code to physical robots. Then, once the code is ready, development teams can use AWS IoT Greengrass to automatically deploy release code to test fleets of real robots for further testing and validation. And then finally, to their production robots in the field. AWS RoboMaker enables developers to run their high-fidelity simulations with a simple API call. Developers can bring their own applications running in containers and use the simulation engine of their choice, from common ROS simulation tools like Gazebo and Arviz to game engines like Unreal. Then, once running, they can interact with the GUI-based applications over a browser. Developers can also set custom S3 upload locations for data and log files to capture and process after the simulation jobs have completed. And finally, they can use AWS RoboMaker WorldForge to procedurally generate 3D environments with different floor layouts and furniture configurations. We've recently released a new set of features that enables running custom simulations in AWS RoboMaker. Developers now have access to a GPU core to run high-fidelity simulations, such as this example, which shows the Carla simulation running with Unreal Engine in RoboMaker. You simply build and select a container image with the simulation stack you want to use, and you can then add your application container, and you can now run any ROS distribution or a completely custom robot application stack. So there's multiple benefits to running simulations in the cloud with AWS RoboMaker. First is access to scale. The service automatically scales the amount of compute required to run the simulation up to 15 virtual CPUs, sorry. In addition, these can be horizontally scaled by running hundreds of simulations with a single API call. RoboMaker provides enterprise-grade availability as well, and built-in health checks to ensure simulations run smoothly and reliably. RoboMaker also provides the flexibility of running any simulation stack and containers. It still manages provisioning the required GPU and CPU resources on your behalf. RoboMaker is integrated with multiple other AWS services, enabling you to easily extend your cloud functionality with things like CloudWatch logs, machine learning services, data storage and analytics services, and more. Finally, with pay-as-you-go pricing, you only pay by the minute for the resources you consume. All right, so let's get started. I prepared a sample application to show you today using the Carla simulator, an open source simulator for driving research. We've created a simple simulation that will spawn an autonomous vehicle and will give it a waypoint. Once the vehicle has reached its destination, the scenario-based test will be complete. Let's run the first test at real time, where 1 second of simulation is 1 second of wall clock time. You'll see the autonomous car here navigating around the roundabout and reaching its destination with some stats returned once the simulation is complete. So there you saw it complete its test. And now we're going to run it faster at 20 frames per second. You'll see it come around the roundabout here a little bit faster, and even everything in the simulation is running at now 1.7x. Now let's dig into how to build and run this simulation in RoboMaker. I've created a development environment in AWS RoboMaker to build the Carla simulation container. You could also do this on your own local machine, but let's open the development environment. The first thing to see here is the Docker file that we are going to use to build our container. To run in RoboMaker, you'll need to bring an OCI compatible Docker image and define an entry point. For more details on how to configure your Docker image, you can please see our documentation. In this Docker file, you'll notice we're referencing a Carla Sim base version, base image. So let's run with this. Let's run this in RoboMaker in the cloud. Okay. In order to do that, we need to create a repository in Amazon ECR, which is our Elastic Container Registry. Once it's in the registry, then we can send it to RoboMaker and launch the simulation. So now you see we've just built the container and we've tagged it. Now we're going to do a push to Amazon ECR. We've just done the push. Once the push is complete, we can now go to the RoboMaker console and launch the simulation. So now we go to RoboMaker, Simulation Jobs, Create Simulation Job. We'll choose a software suite. In this case, since we're bringing our own, it's called General. We choose an IAM role for this purpose. We're going to select CPU and GPU. And here's where you can choose your number of simulation units. You can also select what simulation job output you want. We're going to set up our network using our default VPC, default security group, and select a couple subnets in our region. You also have the option to add additional data sources if you like, and add tags. We're not doing that for this particular simulation run. You can also add a robot application. We're not going to do that for this run. We're just going to specify a simulation application. So this is going to be based on our already uploaded container. So we'll call this Carla Simulation Demo. And we're going to choose the simulation runtime as our software suite. Now we browse ECR to find our container image. It was called Carla Examples. Okay, select the latest version of that. Next, we need to specify our launch command. So this is what gets launched inside the container to run the simulator. We choose Run with Streaming Session. This is how we'll get to see the GUI when we're running the simulation. We have the option to set environment variables. We're not going to do that for this run. And you have option to set up various simulation application tools. So we will set up a couple tools here. We're going to set up a couple Xterms. So we go to Customize Tools, Add Tool, put in tool name Xterm, and then put in the command to run. So that's user bin Xterm here. We choose our exit behavior to be restart, and that will restart the tool if it goes down for any reason. We're going to do this a second time. We want to have two Xterms available to us in case we want to run two different applications at once, two different tools at once. You also have the option here to add additional port connectivity, port mapping basically, and specify uploads configurations for log files if you want to store your logs at the end. Now we click Create, and it will say that the job is being created. It usually takes a couple minutes, so we're skipping some of the delay here in this, and now we've got the simulation running. From here, we can now view our Xterm and our simulation application. Now seeing those appear here, the simulation is running on the left, and we have our Xterm on the right. we're going to run our example application here, which will run our autonomous vehicle as we did before. It's going to send it to a waypoint, so it's going to come around the roundabout here, and we're running at real-time speed right now. So 1 second of simulated time equals 1 second of wall clock time. And here comes the car. As you can see, everything is running as expected. Now we're going to run this again. This time we are going to speed it up. So in order to do that, we need to pass a parameter into our example faster script. And the name of that parameter, let's see, it is sim time resolution. So we'll run this script again with sim time resolution and set that to 20. And once we run it with sim time resolution of 20, it will run at a faster than real-time rate. So here we set that to 20. Now it's going to run the exact same simulation as before. Now it's doing it at 20 frames per second. And here comes the car. And you can see the entire simulation is actually moving faster. We didn't just speed up the car. We sped up the clouds, the water, everything in the simulation. You also have the ability to see things like how many simulation units are running and how much memory you're consuming during the simulation. You have the ability to see logs and see all the other parameters you've set for your simulation application from the RoboMaker console. So that concludes our first demo. So now let's move to the next phase here. Let's tell you a little bit about the RoboMaker CLI and the SDKs. So while the console presents a nice user experience to launch simulation jobs, in many cases, developers want to programmatically run simulations using the API. So AWS provides both a command line tool as well as a variety of different SDKs, which allow you to enable this. So you'll notice that the same parameters that we defined in the console are available to be set in the command line. The ones to note are the max job duration in seconds, the IAM role, the simulation job we use to connect to AWS services, the robot application and simulation applications, which are references to your container image in ECR, and the compute type, such as CPU and GPU. If you want more information on how to structure the parameters for the SDKs and the CLI, you can see our documentation. In addition to running a single simulation job, AWS RoboMaker also has a batch API to run many simulation jobs. One key thing to note with this simulation job batch CLI command is that create simulation job requests. This is an array of the single job request parameters from the previous slide. So you can build single jobs and then you can put them in an array and call them through our batch API and run them in parallel. For those of you new to AWS, you can also store parameters in a JSON file and reference the file in the CLI command. Since batch requests can have a large number of parameters, this can cut down on the amount of work you have to do. Okay, so now let's walk through a batch simulation example. Here's a completed simulation batch that we'll run today. We're going to run 3 concurrent simulations, each with different real-time factors, and then review the results. So let's see what the results look like for a single simulation job in this batch. We're going to look at the tags here because in this example, we publish results by adding tags to the simulation job. So you can see there's one that says that the test passed, and you can see the real-time rate was 1.0. Now let's go back to our IDE, and you can see here we have our JSON config file, which tells you what your compute type is. It tells you this is where you specify the application you're using, the Carla examples application, and the command to run that. And then we have a tool called runtest.sh, which actually runs the test. So let's go look at run test.py, which is called by that. And from within here, you can see the code that, this is Python code that tags the RoboMaker sim job with the proper tag values, and then also cancels the job when it's timed out. Okay. Now that we've seen that, now let's run the job. So here's the CLI to run it. It's RoboMaker start simulation job batch with our batchconfig.json, and that starts the batch file. Now back in the console, you can see now we have 3 jobs that are in the preparing state. These will take a few seconds to prepare. Then they will all run. Once they're completed and terminated, then we can go look at the results. So now they're running. Okay, they've just terminated. So now we can go in and look at the tags and see the results of what happened. Okay, so now we were looking at the first job within the batch. You can see the sim time resolution in this one was 20. So the real-time rate on that was 1.6. So it ran 1.6 times real-time. So the time elapsed was 18, well, it only took 18 seconds to run a 30-second simulation. Now, if you look at the next one, the sim time resolution was 0, and that means that it ran in real time. So the real-time rate was 1.0, and the simulation time and the wall clock time match. All right, we'll finish our talk today by highlighting how companies like Lunar Outpost can bring together these tools to build fully automated CI/CD pipelines. AWS Code Pipeline is a fully managed continuous delivery service where developers can define and run a set of actions at each stage of your release. First, developers work on a feature branch and implement new functionality. Using the RoboMaker IDE, they could have a consistent development experience and access high-powered compute for iterative development with simulation. Once the feature is ready, then they submit a pull request. The pull request gets reviewed and then merged into an integration branch. This starts the first 2 stages in the CI/CD pipeline. First, the source code is copied into a build server running an AWS code build, a fully managed CI tool that will run the Docker build commands, and then copy the built container into the Amazon Elastic Container Registry, a central repository of container images. Once the container images are built and published, the next step is to run the batch of automated tests in RoboMaker Simulation. The test results are automatically copied from RoboMaker Simulation to an Amazon S3 bucket, where they can be aggregated, analyzed, and visualized using AWS Athena and Amazon QuickSight. Once the tests in the simulation pass, the new container images can then be automatically deployed to real robots. Results from the tests on real robots can also be uploaded to S3, then combined with the simulation test results. After all of these tests and validation checks pass, the code can be merged into a release branch and then deployed over the air to the production fleet. So as we close, here's a quick recap of what we've covered today. We talked about how simulation is a critical part of robot application development and testing. It can speed up development cycles and lower the cost of mistakes. Using simulation can speed up release velocity by catching software defects early and enabling comprehensive testing. We showed how to run high-fidelity simulations in AWS RoboMaker using these new features that support GPU and the flexibility to bring any simulation software stack with containers. Finally, we highlighted how to run tests in batches and how to include automated simulation-based tests in a CI/CD pipeline. If you're interested in these solutions and more, please check out our blog and documentation. To learn more about Lunar Outpost, their upcoming missions and latest updates, take a look at their website and various social media channels. Thank you very much.